In April 1944, Allied bombing raids struck Munich. Among the buildings destroyed was the Bavarian State Collection of Paleontology. Inside that building were fossils that had been excavated from the Egyptian desert over 30 years earlier by a German paleontologist named Ernst Stromer. They were the only known physical remains of a dinosaur Stromer had discovered and named in 1915. Those fossils were gone, and for the next several decades, that dinosaur, already one of the most unusual animals ever described, was known almost entirely from old notes and technical drawings. The dinosaur was Spinosaurus, and the story of what it actually was, how it lived, and what it could do has been rewritten so completely over the past 2 decades that researchers who have spent careers studying large predatory dinosaurs have had to revise assumptions they had held for most of their professional lives. Spinosaurus aegyptiacus lived roughly 95 to 100 million years ago in what is now North Africa, during the middle of the Cretaceous period. At the time Stromer found it, paleontology already had a reasonably clear picture of what large predatory dinosaurs looked like. Tyrannosaurus had been described in 1905. Allosaurus had been known since the 1870s. The body plan for a large meat-eating dinosaur was becoming established: bipedal, walking on powerful hind legs, with a deep skull, heavily serrated teeth, and a rigid tail that counterbalanced the forward weight of the body. Spinosaurus did not fit that picture. The skull Stromer found was long, narrow and low, shaped far more like the skull of a large crocodilian than like T-Rex. The teeth were conical and rounded. The spines projecting from the vertebrae of the back were unlike anything previously recorded in a dinosaur, some reaching close to 2 meters in height. Stromer described it carefully, published his findings, and placed the fossils in Munich, where they were studied and debated by other researchers for decades. When the bombing raids of 1944 destroyed the collection, they eliminated the primary physical evidence for a species that was already generating more questions than answers. Stromer had written to the museum director before the raids, requesting that the most significant fossils be moved to a safer location. The request was not granted. He learned about the destruction of his collection when reports of the raids reached him. He died in 1952, outliving the fossils by 8 years without ever seeing the questions he had raised about Spinosaurus resolved. Before getting into what made Spinosaurus genuinely unusual, the raw dimensions need to be stated clearly because they establish the scale of what is being discussed. Based on the most complete specimens analyzed, Spinosaurus reached lengths of 14 to 15 meters. Weight estimates range widely depending on body mass modeling assumptions, but credible figures fall between 7 and 14 metric tons. For comparison, the largest T-Rex specimens reach around 12 to 12.5 meters and approximately 8 to 9 metric tons. Carcharodontosaurus saharicus, another massive theropod from roughly the same era, was similarly sized to T-Rex. Spinosaurus was larger than both by a meaningful margin. It holds the position of the largest predatory dinosaur currently known from the fossil record, and that record, as of the most recent major analyses, remains unchallenged. The size by itself would be enough to make Spinosaurus notable, but an animal can be large and still conform to the established body plan for large theropod dinosaurs. Spinosaurus did not conform to that body plan in any significant respect. Every major anatomical feature, the skull, the teeth, the limb proportions, the bone density, the tail structure, was either unusual or, in some cases, unprecedented. The skull of Spinosaurus is the most immediately telling piece of its anatomy. In large predatory dinosaurs like Tyrannosaurus and Carcharodontosaurus, the skull is relatively deep and broad, built to generate crushing force in a vertical direction. The teeth are laterally compressed and serrated, designed to shear through flesh and sometimes bone. Spinosaurus had a skull that was long, narrow and low-profiled, with estimates placing the total length at around 1.75 meters in the largest specimens. The snout extended forward in a shape that closely resembles what you see in modern gharials, the long-snouted Indian crocodilians that specialize in catching fish. The teeth were conical and rounded in cross-section rather than flattened and serrated. Conical teeth are not built for shearing through large pieces of flesh. They are built to grip something that is small, slippery, and struggling to escape. Along the sides of the snout and at its tip, researchers identified small pits in the bone. These pits are positioned identically to the neurovascular pits found in the skulls of living crocodilians, where they function as pressure-sensitive receptors. In crocodilians, these receptors allow the animal to detect subtle pressure changes in water, the movement of fish, the vibration of a nearby animal entering the water, disturbances that eyes in a darkened or murky environment cannot reliably detect. Spinosaurus had the same sensory system built into its face, an animal with a skull and dentition calibrated for catching fish, combined with pressure receptors that function specifically in aquatic environments, is making a fairly clear statement about its ecological role. For most of the 20th century, Spinosaurus was illustrated and reconstructed as a large bipedal predator, essentially a scaled-up version of the standard theropod template, with the distinctive sail as a visual feature. The limited fossil material available after the destruction of Stromer's collection made this reconstruction difficult to challenge directly. That changed significantly in 2014 when Nizar Ibrahim and his team published an analysis of new Spinosaurus material from the Kem Formation in Morocco in the journal Science. The specimen, which represented the most complete Spinosaurus skeleton ever studied, revealed a body plan that contradicted the standard reconstruction in several important ways. The hind limbs were short, unusually short relative to the size of the animal. For a 14-meter dinosaur, abbreviated hind legs create mechanical problems that have no good solution on land. They shift the center of gravity forward, reduce walking efficiency, and compromise the balance and leverage that a large terrestrial predator needs to function effectively. They do not create those same problems in water. Short hind limbs on a large aquatic or semi-aquatic animal are unremarkable. Crocodilians have hind limbs that are short relative to their body length because they do not rely on hind limb power for locomotion in their primary environment. The bone density of Spinosaurus was equally revealing. Most large theropods have hollow bones with significant air spaces, a feature that reduces overall weight and allows for faster, more agile movement on land. The bones of Spinosaurus were dense and compact throughout the skeleton, a type of bone tissue called osteosclerosis. In the modern world, osteosclerosis is characteristic of animals that spend substantial time in water: hippopotamuses, manatees, penguins, sea cows. Dense bone functions as ballast, allowing an animal to control its position in the water column without constant muscular effort. A predator that only occasionally waded into shallow water to catch fish does not need ballast. An animal that hunted and navigated in deeper water does. In 2020, a study published in the journal Nature added the final significant piece of evidence about how Spinosaurus moved and where it lived. Researchers analyzed the vertebral structure of the tail across the most complete specimens available, and found something that had not been previously identified in any non-avian theropod dinosaur. The tail of Spinosaurus was laterally flattened, with elongated neural spines that were compressed into a shape functionally equivalent to a paddle. The team ran computational hydrodynamic modeling on the tail structure and found it was capable of generating significant lateral thrust when moved from side to side, the same propulsive motion used by fish and crocodilians when they swim. The study estimated that the tail alone could generate enough thrust to move the animal through water at meaningful speeds. A paddle-shaped tail is a structural commitment to swimming as a primary mode of locomotion, and structural commitments take millions of years to develop. The implications for every previous reconstruction of Spinosaurus were significant. Nearly all prior depictions showed a primarily terrestrial animal that happened to eat fish near water. The 2020 tail study strongly suggested that Spinosaurus was an animal that lived in the water, hunting there, navigating there, and spending the majority of its active life in an aquatic environment. The largest predatory dinosaur that has ever been found was, in all meaningful functional respects, a swimmer. The most visually distinctive feature of Spinosaurus, the elongated spines projecting from its back vertebrae, has generated more debate than any other part of its anatomy. In some specimens, the neural spines of the dorsal vertebrae reach close to 2 meters in height. The first and most persistent interpretation was that these spines supported a thin sail of skin, similar in appearance to the sail seen in Dimetrodon, the ancient synapsid that lived over 100 million years before Spinosaurus. Sails of that kind are generally interpreted as thermoregulatory structures, absorbing solar heat to warm the animal, radiating excess heat in hot conditions. A competing hypothesis proposed that the spines supported a thick muscular hump instead, similar to what you see in modern bison or Brahman cattle, functioning primarily as fat and energy storage. The argument has not been definitively resolved. More recent biomechanical analysis has moved somewhat toward the hump interpretation, partly because the structural demands of a 2-meter thin sail on an animal that spent significant time in water raise practical difficulties. Water movement creates lateral forces on any projecting structure. A thin sail extending 2 meters above the waterline would experience considerable drag and stress every time the animal moved through or entered the water. A muscular hump would be far more mechanically compatible with an aquatic lifestyle. Both interpretations agree that whatever this structure was, it was large enough to be visible from a considerable distance. No other predatory dinosaur of comparable size built anything remotely like it. The North Africa of 95 million years ago looked nothing like the Sahara. The regions that are now Morocco and Egypt were occupied by an enormous tidal flat and river delta system, a vast lowland environment threaded with river channels and shallow coastal waterways draining into the ancient Tethys Sea to the north. The climate was warm and humid. The delta system supported an extraordinary volume of aquatic life. Giant sawfish of the genus Onchopristis, reaching up to 6 meters in length, moved through the river channels alongside large ray-finned fish, primitive lungfish, and coelacanths. Large crocodilian relatives, including Sarcosuchus, which reached around 9 meters in length and weighed close to 8 tons, occupied the same waterways. The ecosystem produced enough large aquatic prey to sustain something the size of Spinosaurus. On the surrounding land, Carcharodontosaurus saharicus, a large bipedal theropod comparable in size to T-Rex, hunted terrestrial prey in the same geographic region. The ecological relationship between Spinosaurus and Carcharodontosaurus appears to have been one of niche separation rather than direct competition. A large semi-aquatic fish specialist operating primarily in river systems and coastal waterways overlaps relatively little with a large terrestrial predator hunting in the drier upland environments adjacent to the delta. The partition is similar to what separates large terrestrial carnivores from large crocodilians in modern African ecosystems. They occupy the same geography, but rarely compete for the same prey in the same habitat. The reconstruction of Spinosaurus across the past century has shifted so dramatically that it functions as a useful case study in how scientific understanding of extinct animals actually develops. In 1915, Stromer described an unusual large theropod with crocodile-like skull features and extraordinary spinal projections. The animal was placed into the framework of known large predatory dinosaurs, strange but assumed to be fundamentally similar in lifestyle and behavior. That assumption persisted through most of the 20th century, supported by reconstructions that gave Spinosaurus the standard upright bipedal posture of other large theropods. The 2014 Ibrahim study demonstrated that the posture, the limb proportions, and the lifestyle model were all incorrect. The 2020 tail study confirmed that the animal was an active swimmer, adapted for aquatic locomotion. Those two papers alone required paleontologists to move Spinosaurus from one ecological category, large terrestrial predatory theropod, to an entirely different one, a large semi-aquatic piscivore with no real equivalent anywhere else in the dinosaur record. The existence of Spinosaurus raises a broader question that has not been fully answered. If the largest predatory dinosaur in the fossil record was a specialist adapted for water rather than land, what else in the fossil record has been misinterpreted because researchers were applying the wrong ecological model from the beginning? Spinosaurus is also a reminder that the conditions under which fossils are preserved, discovered, and studied shape the conclusions drawn from them, sometimes, as in the case of Stromer's bombed collection, in ways entirely outside of science. The original bones are gone. The animal they described kept generating surprises for over a century anyway. That is the story of Spinosaurus, one of the most studied, most misunderstood, and most thoroughly revised animals in the entire fossil record. If you found this video worth your time, please give it a like, share it with someone who would appreciate it, and subscribe to the channel if you have not already. New videos go up regularly, and there is a great deal more in the history of life on this planet that deserves this kind of attention. Thank you for watching.